Here's an example of how we can use a regression-based neural network to predict lead time for a hotel. To give you some context as to the problem that we're going to be trying to solve, we have here a data set for a Portuguese hotel, and as well as factors such as whether they cancel or not, 0 or 1, we also have a variable here called lead time. And lead time is the number of days between when the customer makes their hotel booking and when they are actually due to stay at the hotel. And what we'd like to do is we'd like to use the features that we have here, or at least a few of them, to build a regression-based neural network and predict this variable here, lead time. Let's go back to our notebook. What we'll do is we will work through this notebook, and I'll explain the theoretical nature of everything that's going on as we go through it. Firstly, let's import our libraries. We're getting a few error messages here, but we can ignore them. We're importing the pandas dataset, the dataset that you just saw in the spreadsheet. Now, in our analysis, we have certain variables. Some of them are interval. They can take on a range of values. Lead time is one example. And then we have categorical variables. If we go back to our dataset here, we can see that things like, say, country, market segment, distribution channel, etc., all come as distinct categories. Now, when we run categorical variables, we want to make sure that, first of all, we need Python to convert these into numerical format in order for the neural network to interpret them properly. But in doing that, we want to make sure that we don't unnecessarily induce ranking. For example, we have countries of different customers who have made hotel bookings, some from Portugal, Great Britain, Ireland, so on. And what we want to ensure is that each category is treated independently. We don't want certain countries inadvertently ranked higher than others. As a result, that's why we're using cat codes. The next thing we do is we take our selected features and we put them into a NumPy stack. These features that we've chosen here were selected as part of feature selection processes, which we're not going to go through in this video, but I will provide a link to the entire study if you're interested. Now, before we actually configure our neural network, what we want to do is we want to use what's called the min-max scaler. And if I just go up here, you can see that we imported this library from scikit-learn. Now, what the min-max scaler essentially does is it takes the data and it reshapes it and scales the data between 0 and 1. And the reason we want to do that is because we want a common scale across all of our features. If we have an uncommon scale, then it's going to make the neural network, it's going to make it more difficult for the neural network to interpret the features accurately. As an example, I'll just if we type in y, which is the sorry, just bear with me 1 second. Y1, my mistake. Here's y1. We can see that we have a wide range of numbers here, but let us type in y scale, and now we can see that they're all in, most of them are in decimal format, and they're all bounded between 0 and 1, and that's what I mean by giving the variables a common scale. Now, this is where we configure the neural network itself, what we're doing is we are splitting our training and test data, so the train test split, and we're doing it using the scaled x's and scaled y's. This is our model configuration. Now, before we go further, it's important to understand why we are choosing not only the various activation functions, but also particularly the number of neurons in the input and hidden layers. In this case, we have 11 neurons in the input layer and 2003 neurons in the hidden layer. For the input layer, we need to choose them based on the number of features in the training set plus 1. In the model we have 10 chosen features, so we're adding 1 to that and we're getting 11 input neurons. And what we mean by features are these features here that we've included in the NumPy stack. For the hidden layers, it's the number of training data samples divided by a factor, which can be a factor between 1 to 10, but we're choosing 1 here. Multiply that by the number of input neurons plus output neurons. Because we have 24,036 data samples in the training set, we're dividing that by the factor multiplied by the input neurons plus output neurons, and we're coming up with 2003 neurons in the hidden layer, and we're using 1 hidden layer here. That's going to be sufficient for the majority of problems that you're going to face. And because the output layer is a results layer, we have 1 neuron included in that layer by default. Now let's go ahead and compile the model. Now, before we do that, another important point. There is an inherent trade-off between the number of iterations versus the batch size in any neural network. Now, the batch size is the number of training examples per 1 forward-backward pass, and an epoch is 1 forward and backward pass for all training examples. And there's a trade-off because it means that the lower the number of epochs, the higher the number of iterations are going to be required to complete 1 epoch. And if the batch size is higher, it means that less iterations are required per epoch. Just to illustrate this, we'll use a basic calculator here. 24,036, divide that by 150, 160 iterations. But if we had, say, a batch size of 200, that means 120 iterations required to complete 1 epoch. What we'll do here, let's start off with 30 epochs, and we'll go for a batch size of 100. And let's see what the model results look like. Our model is now being trained. This is a visual of the training versus validation loss. We can see that validation loss is decreasing, but there is quite a bit of volatility there. Now what we're going to do is we're going to take a second data set, H2. Hotel 1 was the training data set. H2 is the set that we are going to use to take the actual lead time. And what we want to do is feed in the data for the chosen features from H2 into the model we built using H1 data, and then compare the predictions with the actual lead time. And it's important to do this because this is the unseen data. This is the test set that we want to use to ensure that the predictions that we're making are actually accurate. And we can't do that with data that the model has already been trained on because we'll bias the model. We'll go ahead and we will import the data for H2 using the same data manipulation procedures as for H1. Again, we're scaling the data, etc. Now, we've made the predictions, and what we're going to do is we're going to assess these predictions on the basis of mean absolute error and root mean squared error. The mean absolute error is 75. Our root mean squared error is 98. And just for context, the mean lead time for the second data set was 109, and the mean predicted lead time is 126. Now, based on the mean absolute error and the root mean squared error, we see that it's coming in lower than the average lead time. But to assess whether the neural network is performing at its optimum, what we can do is we can take note of these results, and we can then modify the batch size and the number of epochs to see will that change. I'll just take a note of this for comparison purposes. Okay. What we'll do then is, let's switch this around a bit. Supposing now we have 100 epochs and a batch size of 30. Will that change our results in any way? I'm just going to go ahead and run the notebook in its entirety here. Again, model is being trained, but this time we've modified the epochs and the batch size. Now we're going to have to wait a bit longer because it's going to take 100 epochs to train. But each epoch is being trained faster because we have a lower batch size for each one. Here's the training versus the validation loss. And if we go to the results, mean absolute error of 77 and root mean squared error of 103. Now, we see that these errors are slightly higher than the first set of errors, and that implies that using a higher number of epochs with a lower batch size has resulted in somewhat worse performance for the model. In this example, we used 30 epochs, 100 batch size, but in this example we used 100 epochs with a batch size of 30. And we can see that the model performance has been a bit worse on MAE and RMSE metrics on that basis. Now, to sort of recap what we've looked at how we can generate a neural network in Python, specifically how we need to scale and prepare our data in order to do so. We've seen the inherent trade-off between epochs versus batch size and how they can influence the model, And we've also taken a look at how we can assess model accuracy using metrics such as the mean absolute error and the root mean squared error. Many thanks for watching. I've provided a link to the GitHub repository for this example, and you can find the notebook there as well as the associated write-ups. If you have any questions, please let me know and I'll answer them as soon as I can. Thank you.